Welcome to our lesson. Today we're going to talk about some basic HBase concepts. In this lesson, we're going to cover the following topics. First of all, we'll introduce some fundamental concepts in HBase, like table, column, Colume family, and so on. Then we come to a detailed elaboration of some HBase operations, such as get, scan, put, delete. And next, we'll take some time to compare HBase and the relational database to help you understand the difference between the two. And finally, we'll focus on HBase shell and introduce some basic shell commands. You can use them to create table, list table, or perform other operations in HBase. We also provide some hands-on practice at the end of the lesson. Before we introduce specific HBase commands and operations, we will start with some design concepts and features of Hadoop and HBase. Most earlier large-scale computing efforts focused on avoiding machine failure by having reliable machines. However, these approaches are very expensive. Google took a much different approach, which was to plan for inevitable machine failure, and perhaps even embrace it by using inexpensive hardware instead. Some papers they published give some insight into their infrastructure, and Hadoop is heavily influenced by these papers. Specifically, Hadoop was developed from papers describing the Google file system published in 2003, and MapReduce published in 2004. This work takes a radical new approach to the problem of distributed computing. One other radical shift they made, and one which Hadoop also takes advantage of, is to reduce I/O bottlenecks by bringing the computation to the data. It will distribute the data across nodes as it is initially stored in the system. And then individual nodes will run programs that process the local data. This minimizes data transfer over the network. In the next few slides, we will discuss some of Hadoop's core design concepts. Now specifically bridge the two thoughts, we have big data and Hadoop. Hadoop is a distributed system aimed at managing big data and handling the issues associated with big data. Let's show how Hadoop handles big data. There are two systems used to handle big data. First is the shared file system, the Hadoop Distributed File System, HDFS. HDFS is built to handle files that are GB or even TB in size and can grow to PB in size. It is highly available with no single point of failure. Another system is the efficient and scalable processing system, MapReduce. It can spread the processing load efficiently across many computers, and it's relatively easy to program with no low-level coding needed. Now specifically bridge the two thoughts, we have big data and Hadoop. Hadoop is a distributed system aimed at managing big data and handling the issues associated with big data. Let's show how Hadoop handles big data. There are two systems used to handle big data. First is the shared file system, the Hadoop Distributed File System, HDFS. HDFS is built to handle files that are GB or even TB in size and can grow to PB in size. It is highly available with no single point of failure. Another system is the efficient and scalable processing system, MapReduce. It can spread the processing load efficiently across many computers, and it's relatively easy to program with no low-level coding needed. Now let's talk about how the ecosystem projects help handle big data. Some other projects add functionality to core Hadoop, like HBase, Spark, Hive and Impala, Scoop, and Flume. HBase is a highly available and scalable database. It provides very large throughput to handle a massive user base and can store massive amounts of data. There may be GB, TB, or even PB of data in a table. Spark is an alternative to MapReduce. It is faster and easier to use. It can process streaming data. Hive and Impala are SQL-like language. It allows us to process big data using a familiar language SQL. And you can analyze data without needing to be a programmer. Scoop and Flume are tools to ingest the data from external systems. Data held in RDBMS or being generated on the fly can be easily imported into Hadoop with these tools. HBase is a NoSQL database that runs on top of HDFS. It is an open-source Apache project. This project aims to design a system that can host very large tables with billions of rows and millions of columns. HBase is an open-source, distributed, versioned, column-oriented storage system modeled after Google's Bigtable. HBase is highly available and fault-tolerant, very scalable, and can handle high throughput. It is able to handle massive tables and well-suited to sparse rows where the numbers of columns varies. HBase is based on Google's Bigtable, but it has many different features. HBase helps solve data access issues where random access is required. HBase also can scale easily, making it ideal for big data storage and processing. Columns in an HBase table are defined dynamically as required. Now let's see some use cases of HBase. First, because of its high capacity, you can use HBase to store the entire Internet. For example, Yahoo is a big user of Hadoop and HBase. They are using HBase to store the entire Internet. It stores massive amounts of data, from hundreds of GB growing to TB or even PB. Secondly, it provides high read and write throughput. Its throughput can reach 1,000 operations per second per node. Facebook runs entirely on HBase. There are 75 billion operations per day in Facebook, and its peak usage is 1.5 million operations per second. HBase provides scalable in-memory caching. Every node in the cluster has a cache associated with it. As metadata and blocks are written, they are cached. Although there is a large amount of stored data, queries often access a small subset. Since data is cached in memory, it speeds up queries by reducing disk I/O. HBase also excels at key lookup, and there is no penalty for sparse columns. You can use HBase when you need random write, random read, or both. And if your application performs thousands of operations per second on multiple TB of data, you can use HBase. When you use HBase, your access patterns should be relatively simple. But in the following cases, HBase won't be a wise choice. For example, if your application only appends to your dataset and tends to read the whole thing when processing, in this case, please don't use HBase. And if the primary usage is for ad hoc analytics, HBase won't fit. And thirdly, if your data easily fits on one large node, it is not recommended to use HBase. HBase does not provide certain popular RDBMS features. First of all, HBase doesn't provide integrated support for SQL, but there are many external projects such as Hive, Impala, and Phoenix providing various ways of using SQL to access HBase tables. Secondly, it doesn't support transactions. And third, there are no multiple indexes on the table. And finally, it is not compliant with ACID. Designing an HBase application requires developers to engineer the system using a data-centric approach. This is a less familiar approach. The relationship-centric approach is more common. Above all, we introduced some basic design concepts of Hadoop and HBase. We learned Hadoop is a distributed system aimed at managing big data, and its core components are HDFS and MapReduce. HBase is a NoSQL database that runs on top of HDFS. It allows for large tables and high throughput and requires a data-centric design approach. Next, we'll come to a specific introduction about HBase tables, rows, columns, and so on. HBase is an open-sourced, distributed non-relational database. It is designed for massive scalability, so it can store unlimited amounts of data in a single platform and handle growing demands for serving data. HBase also stores data in tables, but it has some different features from the traditional relational database. In HBase, table data is stored on Hadoop Distributed File System. Data is split into HDFS blocks and stored on multiple nodes in a cluster. HBase tables are comprised of rows, columns, and column families. Every row has a row key for fast lookup. Columns hold the data for the table. Each column belongs to a particular column family. A table may have one or more column families. Because HBase is designed to use multiple machines to store and serve table data, so it is distributed. HBase stores table data as a map. This guarantees that adjacent keys will be stored next to each other on disks. Every row in an HBase table has a row key, which is similar to a primary key in other systems. The row key is an arbitrary string, typically 100 bytes or less. The rows are stored in lexicographic order by row key. Be careful with numeric row keys. If your row keys are 1 to 10, they would sort as 1, 10, 2, 3, 4, 5, 6, 7, 8, 9. To ensure that they sort numerically, they must be left padded with zeros. Columns are grouped into column families. A table has at least one column family. It is advisable for a table to have a small number of column families. These column families are not easy to change, so it is advisable to choose wisely. A column family may have any number of columns. Columns are not predefined, so you can add columns on the fly. They are different from the columns in the traditional relational database because they are arbitrary labels. The data in columns is non-typed. Columns hold the data for the table. You can create column on the fly. The columns in the same column family have the same prefix. You can change the storage setting for each column family. For example, the number of versions of each cell to be stored. The major difference between HBase and a relational database is that in HBase, columns are created on the fly. In relational database, all columns must be created when you create the table. A column is referenced using its column family and column name or qualifier. You should use separate column families when data is not frequently accessed together, or data uses different column family options like compression. HBase supports a bytein and byteout interface via put and result. So anything that can be converted into an array of bytes can be stored as a value. Input can be strings, numbers, complex objects, or even images, as long as they can be rendered as bytes. There are practical limits to the size of values. For example, storing 10 to 50 MB objects in HBase would probably be too much. In general, file size should not be over 10 MB. Data is physically stored on disk on a per-column family basis. Empty cells are not stored. An HBase table is sorted map. Actually, each column family is a separate sorted map. The map key is row key plus column plus timestamp. The value is the cell contents. The rows in the map are sorted by key. Data in HBase is non-typed. Everything is an array of bytes. Rows are sorted lexicographically. For numeric data, this means 1, 2, 3, and 10 would order 1, 10, 2, 3. In order to have numbers sorted in numeric order, left pad the values with zeros to ensure they are in the same length or store them as binary.